After studying this module, you shall be able to understand the point which can simplify the complex spectra, understand the double irradiation and nuclear Overhauser effect, understand how the use of Lanthanide shift reagents and chiral resolving agents affects the appearance of an NMR spectrum, and also you will understand the effect of temperature on the NMR spectrum of cyclohexanes. Let us begin with the introduction of simplification of the second order spectra. The complete analysis of a NMR spectrum becomes difficult when signals overlap, and hence useful information is buried due to complexity of the spectrum. For example, if several closely related methylene groups are present in a molecule, their signals may overlap and the signals would not be clearly recognized in an unsimplified NMR spectrum. There are some important methods to simplify a NMR spectrum and get the maximum information in order to simplify the spectra and also to elucidate the compound in a better way. Let us now come on to the main topic, which is the high field strength, one of the ways to simplify the spectra. As we know, students, that the chemical shift measured in Hertz is directly proportional to the applied magnetic field, whereas the coupling constant remains the same. Thus, on increasing the field strength, the value of delta nu by J will increase further and gives more separation between individual multiplets overlapped at lower field strength. Thus, the NMR instruments with high field strength give better resolution and therefore they are easily interpretable. In the figure which is given, I will discuss it. NMR spectra of C3H5ClO have shown at 100 and 500 MHz instruments respectively. It is clear that at high field strength, that is of 500 MHz, the multiplets are having larger separation and thus giving higher resolution and a better resolution. Now you can see how the resolution changes and how the spectra looks much better at 500 MHz than when it is done at 100 MHz. Students, we shall now take up solvent effects in simplification of a spectra. Chemical shift depends on the solvent which is used to record the NMR spectra. The interaction between the solvent molecules and the solute molecule may shift the resonance position of a proton. If the solvent is non-polar, such as hydrocarbons, there will only be van der Waals forces or weak London forces interactions between the solute and the solvent molecules, and hence the chemical shift of the protons in a molecule will remain the same or very minute changes will occur. However, students, if the solvent is polar in nature, such as acetone, chloroform, DMSO, etc., strong dipole-dipole interactions between solvent and solute molecules would occur, especially when the solute molecules also contain polar bonds. Because of these strong interactions, the observed chemical shift will shift to a greater extent with respect to that taken in the nonpolar solvent. If the solvent has a strong diamagnetic anisotropy, let's say for example benzene, pyridine, etc., the interaction between the compound and the anisotropic field of the solvent may give rise to a remarkable shifting in the resonance position. It is observed that the solvents such as benzene or pyridine, they cause the shifting of observed resonance to the lower delta value, whereas other solvents such as acetonitrile results in shifting to higher delta value. This difference is believed to be depending on the shape of the solvent molecules, which affect the nature of the solute-solvent interaction in the solution. Aromatic solvents are flat molecules, while acetonitrile has a rod-like shape. Thus, we can use these solvent shift effects to resolve the complex spectra to some extent. By adding a small amount of deuterated benzene or pyridine to the NMR sample, we can cause a dramatic difference in the appearance of the NMR spectrum of that particular compound. The overlapping multiplets can be separated from one another and hence they can be analyzed more accurately. Next, we come on to the study of deuterium exchange reactions, that is deuterium, which is the heavier isotope of hydrogen and which can help in the simplification of the spectra. Deuterium exchange is the most elementary and very useful technique for assigning the protons of hydroxyl, amine and SH, that is thiols, etc. groups which are exchangeable with deuterium. We have put this reaction here, as you can see, for the exchange of the hydrogen with deuterium. Due to the reactions, the peak due to the alcoholic hydrogen will disappear and a signal due to HOD proton will appear in the spectrum. For detecting the protons exchangeable with D2O, either the spectrum is recorded in D2O or a few drops of D2O are added to the sample and the sample tube is shook properly before recording the NMR spectrum. The deuterium is not detected in the proton NMR as it absorbs at a different field strength and hence there will not be any coupling or splitting due to the proton which has been exchanged with deuterium. Let's come down to the topic of spin-spin decoupling or double irradiation or double resonance for the simplification of a complex spectra. The spin-spin coupling between neighboring nuclei results into the signals splitting, causing different multiplets. However, in certain cases the splitting patterns are very complex. The spin-spin decoupling technique is used to simplify the NMR spectra. In the spin decoupling, a second strong radio frequency is generally applied while the spectrum is scanned in the usual fashion. This radio frequency can be set to irradiate a particular group of equivalent hydrogens in the molecule. Irradiation with high energy radio waves causes a rapid transition among their nuclear spin states. Thus, the neighboring protons cannot see different spin states of the irradiated protons and consequently any spin-spin interactions are effectively removed and thus you have a simplified NMR spectrum. Now for this, consider an example of 1-bromopropane to understand the concept of spin-spin decoupling. Now here you can see how that particular proton which is marked is particularly irradiated and how the spectra of 1-bromopropane is thus simplified to get a simplified NMR spectrum using the spin decoupling technique. The figure basically shows the effect of double irradiation of the alpha CH2, beta methylene and the gamma methylene protons. If the protons at alpha carbon are irradiated, the signal due to these protons will be collapsed and hence no coupling will be observed due to these protons. Therefore, the protons at beta carbon will be observed as a quartet due to coupling with methyl protons only, and the methyl protons will appear as a triplet due to coupling with the adjacent methylene protons. The irradiation of beta methylene and gamma methylene protons and the changes in the signals due to other protons can be explained in a similar way. Now students, let us come to the topic of use of lanthanide shift reagents which help in the simplifying of NMR spectrum. The lanthanide shift reagents were first introduced by Hinckley in 1969. When such reagents are added to the compounds which are under investigation by NMR, there is a remarkable shift in the resonance positions of the protons in the molecule without increasing the strength of the applied magnetic field. That is, a second order spectrum is generally converted into the first order spectrum. Now here we have shown you some of the lanthanide shift reagents in this figure. The lanthanide shift reagents are beta dicarbonyl complexes of rare earth metals, also known as the lanthanides. The commonly used lanthanide shift reagents are tris 1112233, heptafluoro 77 dimethyl octane 46 dionato-europium. Also you can just abbreviate it as EUFOD whole thrice. And another one is tris dipivloyl methaneto-europium, or you can abbreviate it, students, as EUDPM whole thrice. The lanthanide shift reagents are mild Lewis acids which attach themselves to sites which have lone pairs such as amines, hydroxyls, aldehydes, ketoses, thiols, ethers, etc. The amount of shift in the resonance position depends on the lanthanide metal ion, proton under investigation, and concentration of the shift reagent in the solution. More is the availability of the lone pair, greater is the complexation. The strength of the complex formation is in the order, provided the complexation site of the molecule is not sterically hindered. First we have the amine, then it begins with hydroxyl, which is less than the carboxyl, then the ether, then the ester, and then the nitrile. That means the highest complexation facility is with the amine and the lowest is with the cyanide or the nitrile. The simplification of complex spectra by the addition of shift reagents can be explained by the example of 1-hexanol. In the absence of a shift reagent, as described to you above, the spectra of 1-hexanol looks like as is shown in this figure. We can clearly see only the signals due to the terminal methyl protons, that is a triplet at delta value of 0.9 ppm, and due to the methylene group next to the hydroxyl group, that is a triplet at delta value of 3.8 ppm. Now the remaining methylene protons come into a broad and an unresolved peak between 1.2 to 1.8 ppm of delta value. On adding the shift reagent, the signals due to the methylene protons which are closer to the hydroxyl group are shifted downfield, that is towards the left hand side of the NMR spectrum, resulting in clearly observable signals. The methylene group, which is relatively more closer to the hydroxyl group, is shifted more downfield, and as the distance of the methylene groups increases from the OH group in 1-hexanol, shifting of the peak is less pronounced in presence of a shift reagent. Thus, on addition of shift reagent, spectrum is simplified to almost of the first order, and you can more appreciate it by seeing this unsimplified and simplified spectra by addition of the shift reagents. And this shift reagent is only 6.5%, that is the concentration is 6.5%, and here we have used EU, FOD, the europium is, and the FOD whole thrice as a shift reagent. Now let us study about the chiral resolving agents for the simplification of the NMR spectrum. The NMR spectra of the enantiomers are identical. In some cases, however, an optically active solvent may cause chemical shift difference between resonance positions of the two enantiomers, but the amount of shift is often too small to be utilized for the analysis of complex spectrum. The enantiomers can thus be distinguished by running their spectrum in the presence of a chiral shift reagent. Now, when a racemic mixture, that means having a pair of enantiomers, is treated with an optically pure chiral resolving agent, a mixture of diastereomers is obviously formed. Thus, the protons will become chemically non-equivalent. That is, diastereotopic protons will have a different chemical shift. Suppose we have a mixture of R and S isomers of alpha phenyl ethylamine. When an optically pure chiral resolving agent like S plus O-acetyl mandelic acid is mixed with the mixture, two diastereomers become, that is, RS and SS. Now the methyl group has become diastereomeric and the chemical shift of the methyl protons in both the diastereomers will be different. Here in this particular case, students, two doublets each for one diastereomer will be observed in the NMR spectrum due to the methyl protons. The integration of the two doublets can determine the percentage of the R and S isomer in the particular mixture. So now you can very well appreciate that even IR spectroscopy cannot differentiate between enantiomers. However, using the chiral resolving agents, we can differentiate between two enantiomers in NMR spectroscopy. Now comes a very important effect in case of NMR, also known as the nuclear Overhauser effect, and how it will simplify the NMR spectrum we will study. The nuclear Overhauser effect, students, was first introduced by Overhauser in 1953. This effect is a change in the intensity of a signal due to a particular proton on double irradiation of nearby protons within the molecule. In this case, less intense radiation is used than the spin-spin decoupling or double irradiation. An increase of few percent in the intensity of absorption is observed between protons which are in close proximity. It is generally observed over very short distances, that is only 2 to 4 angstrom. NOE, as it is abbreviated, and spin-spin decoupling, as I have previously told you, are two different concepts. NOE is the interaction of the nuclei through space, and the number of intervening bonds between the concerned protons has no significance, whereas spin-spin decoupling takes place via the bonds which are separating the nuclei. NOE is associated with dipolar relaxation mechanism. A spin-excited nucleus may undergo spin relaxation via the transfer of its spin energy to the nuclei in close proximity. The efficiency of this process is directly related to the distance between the two nuclei. If we irradiate one of the nuclei, the intensity of the nucleus closest in space to the irradiate nucleus will be enhanced in comparison to those which are far removed. Thus, NOE may be useful in studying the stereochemical relationship between various molecules. To understand the phenomena of NOE, let's take an example, students, of 3-methyl-2-butanoic acid. If the vinyl proton Hc is irradiated, the intensity, that is the integral value of the cis-methyl group, becomes greater than that due to trans-methyl group. Similarly, on irradiation of the cis-methyl group, the intensity of the Hc increases, whereas the irradiation of the trans-methyl group, which is at more distance, does not affect the intensity of the Hc signal. In isovanillin, which is another example, irradiation of O-methyl group, that is O-methyl protons, the integral of the Ha proton, in case which is a doublet, is increased due to NOE. In example 3, which is shown here, on irradiation of CH3 protons, the intensity of hydrogen, as depicted figure, increases. Now you can see we have given here 3 structures, and whatever I have explained here relates to all the 3 structure which is given. The last structure belongs to vanillin. Now let us study the effect of variable temperature NMR for simplifying the NMR spectrum. As we already know, students, that the protons in cyclohexane are of two types, axial and equatorial. Axial protons in this figure have been shown here in red, and they occupy a different electronic environment than the equatorial protons, which are shown in blue. That means axial and equatorial protons are not chemically equivalent. Hence, one can expect two signals for proton NMR spectrum of cyclohexane, one for 6 axial protons and the other for 6 equatorial protons. The NMR spectrum of cyclohexane shows only a single sharp peak at delta value of 1.4 ppm. Now, how is that possible? This can be explained by the fact that at room temperature, the rate of ring flipping is so high that you cannot observe two different signals, that is one for axial protons and the one for equatorial protons. The NMR spectrometer is too slow to acquire a spectrum of the individual conformations of cyclohexane and can only detect the average electronic environment produced by the protons, and hence only one signal can be observed. The single peak observed has a chemical shift in between the actual chemical shift, which is of the axial and the equatorial protons. The rate of ring flipping can be slowed down by decreasing the temperature. If we cool this sample of cyclohexane to -100 degrees Celsius, ring flipping occurs at a very slow rate, and thus separate signals are observed for both axial and equatorial protons. Now you can see, since both of them are in equilibrium and at this temperature of -100 degrees Celsius, you can actually observe two signals, one for the set of all axial protons and another for the other set of equatorial protons. Now students, let us summarize this module. In this module, you have learned that a chemical shift is measured in Hertz and is directly proportional to the applied magnetic field, but the coupling constant does not. You have also learned that the NMR spectrum taken at higher field strength gives us a better resolution as compared to that taken at a lower field strength. If you remember, we have taken an example of a spectrum taken at 100 and 500 MHz. The chemical shift values vary with solvents to some extent. Hence, by changing the solvent, NMR spectrum can be shifted from complex to first order spectra. Then we taught you the spin-spin decoupling technique can be used to simplify the complex spectra to simple spectra. We have also learned that the non-first order spectra can be shifted to first order spectra on the addition of a lanthanide shift reagents and chiral resolving agents, as these reagents shift the chemical shift values and thus offer higher resolution between the multiplets observed in complex spectra. Nuclear Overhauser effect is very useful in studying the stereochemical aspects of various molecules, and we have definitely taken some very good examples which can show you the difference between nuclear Overhauser effect and spin-spin decoupling also.